Hi, so today we're going to look at writing nuclear equations. We're going to write balanced radioactive decay equations based on what we learned last time. So we're going to review the types of decay, which we talked about in the last video. And I'm going to go over the different types of radioactive decay that there are and show you how to write nuclear equations. First, let's start with reviewing what types of decay are there and what are their symbols. All of this information is provided to you in your reference table in Table O, but you do need to be able to pick out what in Table O is the radiation. There's 4 types, starting with alpha, which uses an alpha symbol, or you could have used the isotope notation as well. Beta decay, gamma radiation, and also positron radiation. So you need to recognize that these 4 are the types of decay, and it's also what we're going to be using when we're looking at our balanced nuclear equations. Natural radioactive decay, so this is what is happening to elements above 82. Elements above 82 are unstable. Their nucleus is going to emit particles spontaneously. No one has to make it happen. There isn't anything that starts that reaction. It's unstable. It's going to break apart. During this process, when that particle is emitted from our unstable nucleus, the element is transmutated, or it changes into another element, which we'll take a look at in our equations. There's 2 types of transmutation. There's natural transmutation, which goes along with the natural radioactive decay. Again, it's a result of an unstable nucleus undergoing one of the 4 decay types. There's also artificial transmutation, which occurs when a nucleus is bombarded with high energy particles. For example, this is what would be occurring in a particle accelerator. This is a man-made transmutation. It's not just occurring outside. For example, this is purposely done, whereas natural transmutation is what's naturally just going to happen no matter what. So when writing balanced nuclear equations, we're going to be using isotope notation. Essentially, the masses, or the atomic masses in the top left corner, are going to have to be equal on either side of our equation. The charges on either side of the equation also have to be equal, because remember, when we're balancing equations, there's a conservation of mass, charge, and energy. And we're going to use table N to determine the type of decay mode for whatever nuclei we're looking at. So again, on either side of our arrow, masses and charge have to be balanced. We're going to take a look at what that looks like. Alright, so the questions are limited to the nuclide given to you in Table N. Table N has a lot of useful information. It gives you the nuclide, it gives you half-life, which we're also going to take a look at later this week. It's going to give you the decay mode, which is what we're going to look at this week. And it also gives you the nuclide name, which is in isotopic notation, element dash the mass number. So you're going to have to use Table N to determine the decay mode. And then you're going to want to use Table O so that it can give you the notation and the symbols that you're going to, or the notation that you're going to have to use. So you're going to have to use both of these tables side by side. So we're going to look at an example of each type of decay and a balanced equation for it. But when we're talking about alpha decay, it means an unstable nucleus is emitting an alpha particle. So you're going to start with your unstable nucleus, and you're going to end up with an alpha particle plus another new element. Here's an example of alpha decay. So we have uranium-235 producing an alpha particle and transmutating into a new element. This is a balanced nuclear equation. If you take a look, the mass on the reactant side of the arrow is 235, If we look at our alpha particle mass plus the mass of our new element, it adds up to 235. So we have 235 on the product side, 235 on the reactant side. Taking a look at the atomic number, 92. If we look at our alpha particle, it's 2 plus 90 to add up to 92. This is balanced. When alpha decay is occurring, again, we start with an unstable nucleus. It's radioactive. It gives off radiation, which is the alpha particle, and transmutates into a new stable nucleus, which in this case is thorium-231. So during beta decay, we're going to lose a beta particle, which is essentially a negatively charged electron. So here's an example. If you look up potassium-42, you're going to see that it's going to go through a beta decay. You start with unstable potassium-42, and you go to this side. It emits a beta particle. You can use an E symbol or the beta particle symbol. But beta particles have 0 mass, which means the mass of the new element has to be 42 in order to balance both sides of the equation. We have 19 on the bottom. Beta particles have a -1, which means to get to 19 to balance, the element number has to be 20, or in this case, calcium. So again, we have unstable potassium. It transmutates into stable calcium and emits a beta particle. So positron, essentially very similar to beta decay, only it has a positive charge. So instead of that -1, it's going to have a +1. For example, if we look up potassium-37 in table N, it's going to go through positron decay. So potassium-37 emits a positron particle. Again, it's an electron with 0 mass but has a +1. And in order to balance out the equation, it has to be 37 on top, 37 on top. We have 19 on the bottom. 18 plus 1 gets us 19 on the bottom. So potassium-37 is going to transmutate into argon-37 and release a positron as its radiation. Let's take a look at a pretty typical question to determine what species X is. So we're missing the reactant or the unstable nuclei from our nuclear equation. The first step that I'm going to do is I'm actually going to figure out what atomic number and mass number that I need to use in order to balance the equation. So if I take a look, I have 208 plus 4 on top for my mass number. Again, mass, charge, and energy are conserved, so it's going to have to total up to the same thing on this side. And I have 82 plus 4 on the bottom. So I know my mass number is going to be 212 and my atomic number is 84. Now I have to go to my periodic table and figure out what the element symbol for element 84 is. So taking a look, and I see element 84 is polonium. So I need element symbol PO. And that means species X is polonium-212. And that would be usually the multiple choice answer. And now I would like for you to give it a try. So in this reaction, sodium-24 is transmutating into magnesium-24. What is the particle represented by X? So if we look at the mass numbers, I have 24 on my reactant side and already have 24 on my product side. So whatever the particle is, it has to have 0 mass. If I look on the bottom, I have 11 on this side and I have 12 on this side. So in order to make it the same on both sides, this is going to have a -1 on the bottom. That means that this nuclei has gone through beta decay which is equivalent to an electron. That's all I have for you today. There's going to be practice questions soon on this. If you have any questions, please let me know.